I'd like to talk about organic acids and bases. Much of this material, I hope, is review from general chemistry. Let's begin with some fundamental definitions. An acid is a proton donor. An acid gives up a proton. It gives up a proton to something, and that something is a base, which is a proton acceptor. An acid that we're all very familiar with is HCl, which I'm writing in kind of a sort of unorthodox way like that, sort of backwards. And a base that I think we're all familiar with would be the hydroxide ion. So this is what we would see in sodium hydroxide and potassium hydroxide. So this is the acid, and this is the base. And what they do is they trade up a proton. So this electron pair on this oxygen removes the proton from HCl. The Cl gobbles up the electron pair in that bond. And so we can picture the transition state for an acid-base reaction with these dotted lines showing that bonds are in the process of being formed and bonds are in the process of being broken. There will be a partial negative charge on the Cl because in the product that is going to pop out with a full negative charge, and the negative charge on the oxygen is in the process of going away. So at the transition state, there's a partial negative on the oxygen. So we'll put it all in brackets and put a double dagger to show that that's the transition state. And then at the end of the acid-base reaction, the Cl minus has formed as a result of the donation of the proton to hydroxide, which has formed water. So that's an acid-base reaction, and how it happens mechanistically is simply the trading off of the proton from the acid to the base. All right, a couple of things to notice about this reaction is that I have been careful to specify equilibrium arrows because the acid-base reaction is an equilibrium process. So that in the forward direction, HCl was the acid, OH minus was in the base, but we have to remember these acid-base reactions are equilibrium processes. They go in one direction. In the forward direction, they also go in the reverse direction. And we see in the reverse direction, Cl minus is now functioning as a base, and water would function as an acid. Water is going to donate its proton to Cl minus, converting Cl minus back into HCl. Now, here we have an illustration of two very important terms when we talk about acids and bases, and that is the idea of conjugate acids and conjugate bases. So HCl and Cl minus, these are conjugates. HCl is the conjugate acid and Cl minus is the conjugate base. OH minus and H2O, these are also conjugates. And a quick and easy way of recognizing conjugates is that the conjugate acid has one more H plus than its conjugate base. So if you look at HCl and Cl minus, they are conjugates. And how are they related? Well, HCl, the conjugate acid, has an additional proton, an additional H plus. So that water is the conjugate acid of OH minus. How do they differ? Water, the conjugate acid, has one more H plus than its conjugate base, which is OH minus. Okay, so those are just some fundamental definitions of acids and bases. So continuing with what is probably a review of Gen Chem for you, continuing to talk about these acids and bases, is that one of the things that is very important about when we talk about acids and bases is acid and base strength, because there is a huge spectrum of acid and base strength. The weakest acid and the strongest acid are separated by 50 orders of magnitude of acid and base strength. I don't mean that the strongest acid is 50 times stronger than the weakest acid. I mean that the strongest acid is a 1 followed by 50 zeros stronger than the weakest acid. So we need to talk about acid and base strength. And this is measured by the pKa, which I hope you remember from Gen Chem. All right, so if we have a generic acid, we'll call him HA, and he's in aqueous solution, so that's just a generic acid. And when we dunk that generic acid into water, an equilibrium is set up where the HA, the acid, is going to donate a proton to H2O, which is going to function as the base. So HA is converted to A minus in aqueous solution. It has served up a proton to water, which picked up the proton and was converted to the hydronium ion H3O plus in the process. So once again, HA is the conjugate acid of A minus. They differ by 1 H plus. H2O is the conjugate base of H3O plus. The conjugate acid H3O plus has one more proton than the conjugate base, which is H2O. Back in Gen Chem, they defined for you the equilibrium constant for a reaction. And remember, the equilibrium constant is a big fraction. In the numerator, you have the concentration of the products, each of them exponentiated to a power equal to the coefficient in the balanced equation. In the denominator, you have the concentration of the reactants, each of them exponentiated to a power equal to the coefficient in the balanced equation. So for our acid-base reaction here, the equilibrium constant would be the concentration of A minus at equilibrium times the concentration of hydronium ion at equilibrium divided by the concentration of HA at equilibrium. So notice that there is no place for the concentration of water in these equilibrium expressions, because if you remember back to Gen Chem, the contribution of liquids and solids to equilibrium expressions is set equal to unity. It's set equal to 1, so that liquids and solids don't figure into equilibrium expressions. Okay, so this is the equilibrium constant. that is set up when we dissolve an acid in water. Another Gen Chem concept that I would remind you of is that if KEQ is greater than 1, that means that products are favored over reactants. And in the context of acids and bases, if the equilibrium constant is greater than 1, that means we will call HA a strong acid. HA is what we would call a strong acid. HA really loves to give up that proton. Products are favored. The product of the reaction is what happens when the proton gives up, when HA gives up a proton to the base. So that when the equilibrium constant is greater than 1, we're calling the acid a strong acid under those circumstances. Conversely, if the equilibrium constant is less than 1, then reactants are favored. And we will say that HA is a weak acid. If the equilibrium constant is less than 1, HA doesn't want to give up the proton. Products are not favored. HA would rather hold on to that proton, and so that will make it a weak acid. Now, I mentioned another thing to notice about this equilibrium expression is, let's say, let HA be a strong acid. We can rewrite the equilibrium in a slightly different way to emphasize that it is a strong acid. We could write something like HA plus water. And now I'm going to put a big, humongous arrow pointing in the direction of the products to show that products are favored. So we'll get A minus plus H3O plus. But we have to keep in mind that the acid-base reaction is an equilibrium process. So there's also a back reaction. But because HA is a strong acid, at equilibrium, there's very little HA left. It's all given up its proton to water, becoming A minus. So I'm going to portray the back reaction with this little wimpy little arrow in this direction. So what this is saying is that a strong acid, HA, has a weak conjugate base. That's a very important concept when we're dealing with organic acids and bases. This guy is a strong acid, but there's a return reaction which is not favorable at all, so that A minus will be a weak base. So that's an important thing to remember. A strong acid is going to have a weak conjugate base, and conversely, a weak acid is going to have a strong conjugate base. So if we let HA be a weak acid, then once again we can write our equilibrium HA plus water, but this time HA doesn't want to give up the proton. So I'm going to write a tiny little wimpy arrow in the direction of product formation. But since it's an equilibrium process, the back reaction will be very strong. So when HA is a weak acid, its conjugate base is a strong base. All right, so those are important concepts to keep in mind when we're talking about acids and bases. A strong acid has a weak conjugate base. A weak acid has a strong conjugate base. I mentioned that the order of acid strengths varies over 50 orders of magnitude. And that's when we consider all kinds of different compounds, both organic and inorganic. When we consider just organic compounds, we also have a huge spread of acid and base strength. So let's just take a little tour of some of the acids and bases that maybe we've heard about and look at what their Kas are. The strongest acid is hydrogen iodide, and the KEQ of that reaction we talked about is 10 to the 10th. All right, so that's pretty big. It's a very strong acid. At equilibrium, there's hardly any I minus left. There's hardly any HI left. It's all been converted to I minus. So sulfuric acid is another acid that we know about. And it's the KEQ for its acid, for its reaction with water is 100. So it's still greater than 1. So this is H2SO4 is still considered a strong acid. Another acid that we are familiar with perhaps is nitric acid. Its equilibrium constant is about 17. So it's still greater than 1. Nitric acid is still a strong acid, but when you compare the acidity of nitric acid to hydrogen iodide, it's already 10 orders of magnitude weaker. Haven't gotten to an organic compound yet. It's not until we get to something like the carboxylic acids. So I'm going to put them over here. The carboxylic acids are among the strongest organic acids, but their KEQs is a paltry about 10 to the minus 5. So most organic compounds are weak acids, but there is a spectrum of acid strength varying over 50 orders of magnitude. So when we get to something like phenol, well, that's also acidic. Its equilibrium constant is now 10 to the minus 10. So it's still considered, when we think of the totality of all kinds of organic and inorganic compounds, it's still considered a weak acid, and it's about 5 orders of magnitude weaker than a carboxylic acid. When we go to a regular alcohol, the equilibrium constant here will be about 10 to the minus 17. And we could just keep going down all of the functional groups. We will in a second. But if we continue, we get to methane, which is among the weakest acids known. And its equilibrium constant for its reaction with water is 10 to the minus 50. So the range of acid strength varies enormously. We don't like to use scientific notation. And because of our aversion to powers of 10 and exponents and that kind of stuff, we would rather be dealing with small whole numbers or smaller numbers. And so we define the pKa, which is equal to the negative log of the Ka. Ka, this is the acid dissociation dissociation, I think I misspelled that, acid dissociation constant. And the Ka is defined as the equilibrium constant of this reaction that we've been talking about, what happens when an acid reacts with water and trades off a proton to the water molecule, becoming A- in the process and converting water to the hydronium ion. So instead of talking about Ka, we like to talk about a pKa. It's simply computationally more simple. All right, so for example, something like Hi, whose equilibrium, whose Ka, as we said before, was equal to 10 to the 10th, its pKa is equal to minus 10. Minus 10 is the negative log of 10 to the 10th. So we notice that a strong acid has a large Ka, but it's going to have a negative pKa. So when we go down to something like H2SO4, its Ka, as we said before, was about 100. So its pKa is a minus 2. So the stronger the acid, the bigger the Ka, but the more negative its pKa. When we get to an organic compound such as acetic acid, its Ka is, as we said before, was 10 to the minus 5. So its pKa is equal to 5. It's now a positive number. And we can continue down that table that I gave you. When we get to methane, its Ka is 10 to the minus 50. Its pKa is 50. So this is the relationship between the Ka and the pKa. So notice that this is going to be the strongest acid. And this guy down here, this is going to be the weakest acid. And so it's important to keep in mind this relationship between the Ka and the pKa. All right. Now, don't expect you to memorize any of these pKas, but memorizing them helps a lot. So instead of memorizing pKas, what I would like to share with you will be this table of pKas. Okay, and so what we see here is, okay, this is the pKas, and on this table, which we're going to learn how to use, we are showing that the proton, we're showing the pKa 50 running down all the way to 5 for an organic compound, and these negative numbers for inorganic compounds. So we have and this table indicates the proton which is under discussion. So the pKa of a proton, just looking at this table here, the pKa of a proton which is bonded to a nitrogen atom in an amine that has a pKa of 35. All right, and now let's say down here, the pKa of a proton, which is bonded to the sulfur atom of a thiol that has a pK of about 10. All right, so let's talk about pKa's and things we can do with pKa's. Things you can do with pKa's. All right, first thing that we can do with the pKa's will be to determine the most acidic proton in a molecule. Because when we say something like the pKa of a carboxylic acid is 5, well, we have to clarify which proton in a carboxylic acid we're talking about. That number, that 5, belongs to a certain proton. But as we know, an organic molecule could have dozens of protons. Which proton is being referred to? That's where our table of pKa's comes in. And so what we need to do is look at that table, look at the molecule, look at the table, and we are matching up the entries in that table to the protons in a molecule. And the one that is going to have the most negative pKa, that is going to be the most acidic proton in that molecule. And that proton, identified in that manner, will be the proton that will be removed first by a base. All right, so let's demonstrate finding the most acidic proton in a molecule. So for example, if I look at this guy, I want to determine, well, which is the most acidic proton in this molecule. I go to that table of pKa's, and I see that one of the entries in that table is for the proton bonded to an oxygen atom in an alcohol, but that alcohol is not a phenol. So I'm cruising down that table and I see there's an entry for an alcohol. So let's see, let's look at that table once again. And I see here I have a proton bonded to an oxygen in an alcohol. But notice this is not a phenol. That's another entry somewhere else in the table. This is a special kind of alcohol that is more acidic. But the molecule that we're looking at here is not a phenol. So that table is telling us that the pKa of a proton on a regular alcohol that's not a phenol is a pKa of 17. All right, now I go back to that table and I see, well, the pKa of a proton on a carbon atom of an sp3 hybridized carbon atom, that's going to be about 50. This guy, looking at that table, is going to be about 50. This one is about 50. This one is about 50. All right. And then I look at that table again, and I see that a proton on the sulfur atom of a thiol, that's about 10. So I've identified the most acidic proton in the molecule, which is going to be this one, which has the lowest pKa. So when this molecule is reacted with hydroxide, it's going to be an equilibrium reaction, but the proton that is removed will be that thiolic proton, the most acidic proton. That is going to be the proton that is going to be removed by the base. So that's one of the things that we can do with our table of pKa's, is that we cruise down that table and we're looking for we're matching up every proton in our molecule with an entry in that table, and that's how we are deciding what the most acidic proton of a molecule is. All right, so I have a couple of comments about that table. Okay, so notes about the pKa table. All right, since this is organic chemistry, and since organic chemistry is the study of the compounds of carbon, there are a lot of entries that have protons on carbons on there. But it's important to be able to distinguish the different situations, because all of those protons are not interchangeable. So I want to make some notes about the use of that table. If the proton is bonded to a carbon atom, and this carbon atom is sp3 hybridized, we're going to find several entries in that table where this situation accrues, where we're going to have a proton bonded to a carbon that is sp3 hybridized, but there are a lot of entries where this happens on that table, so we have to make sure that we understand we're using the right number for the right situation. All right, and so if that sp3 hybridized carbon that has the proton on it, right, it's sp3 hybridized, if it is tucked between two carbonyls, that's one situation. That pKa is about a 10, right? So, but now if we remove one of these carbonyls, we find another entry in that table. Right, this is what is called bis alpha. Don't really need to get into what that means, but that's called bis alpha. That means it's sandwiched between two carbonyls. But now if the carbon is sp3 hybridized and next to just one carbonyl, but that happens to be a ketone, that's another entry in that table. The pKa of this proton now is about 20. But if we change up the carbonyl to an ester, that's yet another entry in that table where we have a proton on an sp3 hybridized carbon. The pKa of this proton is different. It's 25. So what I'm trying to tell you is that we have many situations where we have a proton on an sp3 hybridized carbon, but they're not interchangeable. We have to look at the environment in which that sp3 hybridized carbon is. All right, and then we also have, we could also have a number here for an amide, where now we still have an sp3 hybridized carbon, but now it is the sp3 hybridized carbon, which is next to a carbonyl, which is part of an amide. This guy is at about 30. All right, finally on that table, we have an entry in which the sp3 hybridized carbon is not sandwiched between two carbonyls. It's not next to one carbonyl of a ketone, an ester, and an amide. It's kind of all by itself. It's isolated away from any of these groups. That is considered an alkyl proton, and its pKa is 50, right? So there are several entries on that table that talk about an sp3 hybridized carbon with a proton on them, but they're not interchangeable. We have to find the right situation. Okay, another note about that table will be the proper implementation when we're talking about an alcohol. So something like a proton on a regular alcohol, as we said before, the pKa of this proton is about 17, but when the OH group is bonded to an arene, that's a phenol, its pKa is now about 10. So this could or could not be a confusing situation where we have two different types of alcohols. We have alcohols that are bonded to arenes, OH groups bonded to arenes, and OH groups that are not bonded to arenes. And so that is going to be, that's going to be different pKs. And then if we cruise down that table, we see another situation with another OH group, but now that OH group is the OH group of a carboxylic acid. So this pKa is about 5. So just like we have a diversity of sp3 carbon hydrogen bonds with a diversity of acid strength, we have a diversity of OH bonds with a variation as well of the acid and base strength. All right, so this is one of the things that we can do with the with that pKa table, and with pKa's we can find the most acidic proton in a molecule. So now let's do a more challenging problem. Circle the most acidic proton. All right, so maybe let's cook up a crazy molecule here. Maybe something like this. All right, so what would be the most acidic proton in this molecule? We have to go to that table, or we have to memorize that table to do a problem like this. And what we're doing is we're looking down that table, we're shopping around in that table, matching up every proton in this molecule to an entry in that table. And then the most acidic proton will be the one with the lowest pK. All right, so these protons over here, they are protons on an sp3 hybridized carbon, but this carbon atom isn't any of these types. It's not sandwiched in between two carbonyls. It's not next to a carbonyl either of a ketone, an ester, and a mid. It's kind of just isolated, all by them, isolated from those other groups. So the pKa of these protons is a 50. All right, we're looking at that table, and we see that a proton that lives on a benzene ring, proton that lives on a benzene ring, the pKa's, shopping around on that table, is about 40. So each of these protons have a pK of 40. All right, now there's a proton here as well. There are two of them, as a matter of fact. And now this guy, we recognize these are protons on sp3 hybridized carbon, but this carbon is this type where it's sandwiched in between two carbonyls, so the pKa of that is 10. All right, we found the most acidic proton. It's going to be that one or this one. And when we react this with base, the base is going to remove a proton. It's just going to remove one proton, right? It's not going to remove both of these. It's just going to remove one proton. And so the product of this acid-base reaction would show the removal of the most acidic proton, which is going to be that bis alpha proton tucked between two carbonyls There's our negative sign, negative charge, showing that H plus has been removed by the base, and OH minus, the base, has become this molecule of water. All right, so that's the first thing we can do with the table of pKa's. First thing we can do with pKa's is we find the most acidic proton in a molecule. Next thing we can do with pKa's is we can calculate the equilibrium constant of an acid-base reaction. All right. And we remember that if the equilibrium constant is greater than 1, products are favored. If the equilibrium constant is less than 1, products are not favored, and instead reactants are favored. We're not going to get a big percent yield at equilibrium of a reaction that has a KEQ that is less than 1. So what we use to, we can use these table of pKa's to calculate whether an acid-base reaction is going to give a big percent yield of product, or it's going to give a pathetic percent yield of product. And what we use to calculate the KEQ of an acid-base reaction is we use the Henderson-Hasselbalch equation. I hope you met this equation in Gen Chem. I'm going to give it to you now. You don't have to memorize it, but you do need to know what the symbols of the equation mean, and you have to know how to use it. All right, so this is saying for the acid-base reaction, HA, that's the acid, plus B, that's the base. It's an equilibrium. And what is going to happen here is the acid is going to trade off that H plus to the base. So HA becomes A minus, it gave up the proton. B becomes HB plus, it picked up the proton. So that's just a generic acid-base reaction. The equilibrium constant for the reaction is equal to 10 raised to the power of the pKa of HB plus minus the pKa of HA. And all of this stuff is in there in the exponent. That's the Henderson-Hasselbalch equation. Another way, maybe simpler to understand, another way of writing this equation could be HA plus B minus makes A minus plus HB. So in this version, it's the same. It'll be the pKa, it'll be 10 raised to the pKa of the acid on the right-hand side of the equation minus the pKa of the acid on the left-hand side of the equation. So that's the Henderson-Hasselbalch equation. So let's look at some examples where we're using that. All right, so for example, if we have a carboxylic acid and we want to react that with hydroxide, it's an equilibrium. We want to know what the equilibrium constant of this acid-base reaction is. So this involves a couple of steps. The first thing we need is we have to identify the acid and the base on the reactant side. Well, this is clearly going to be the acid, the carboxylic acid. This is going to be the base. Here it's easy to identify what the acid is and what the base is, but it's not always that easy. One of our big clues is a base is something that reacts with H+, so that if you're looking at a reaction and it has a negative, something has a negative charge on it, that is very likely to be the base, because if you're negative, you love positive. And what a base is doing is reacting in such a way to pick up H+. So clearly this is the base and that is the acid. Okay, so that's the first step, is we have to identify who the acid is and who the base is in our acid-base reaction. Next, we have to identify which proton of the acid will be removed. And so that's where we're running to that pKa table and going through that process that I just showed about how to find the most acidic proton in the molecule. So this is a proton that is sitting next to a carbonyl, right? So this, that table is telling us that this proton has a pKa of maybe about 40. But this is a proton on the OH group of a carboxylic acid. Its pKa is about 5. All right, we found the most acidic proton in the acid on the reactant side. So the acid-base reaction that is going to ensue here will be the removal of the most acidic proton from the acid to produce the carboxylate and water. Okay, now we're ready to calculate the equilibrium constant of this reaction and see whether products are favored here or reactants are favored. All right, so the pKa, that's going to be our Henderson-Hasselbalch equation. We need the pKa of the acid on the right, HB. We need the pKa of the acid on the left, HA. So the pKa of the acid on the left is 5. The pKa of the acid on the right, which is water, that's 16. Where am I getting those numbers from? They're all in that pKa table. The equilibrium constant will be 10 raised to the power of the pKa of the acid on the right minus the pKa of the acid on the left. And so 16 minus 5, that's 10 to the 11th. Oh, that is a whopping huge equilibrium constant. So that when I mix a carboxylic acid with hydroxide ion, I'm going to get a 100% yield of product formation, right? Because that is a huge equilibrium constant. Okay, so let's try this again with some more examples. So here is let's try hydroxide again. All right, so there's an acid-base reaction. First step, identify the acid, identify the base. OH minus, that's the base. Our big clue is it has a negative charge on it. And a base is something that picks up a proton. So this is going to be the base, and this is going to be the acid on the left-hand side of the equation. Next step, identify the most acidic proton of the acid. And that's that process of matching up each proton in the molecule to to an entry in that table. And so I'm concluding that the most acidic proton will be the proton which is next to the carbonyl group of the ester, and its pKa is 25. All of these other protons are protons on sp3 hybridized carbons, but they're not any of those special kinds that we talked about earlier. All of the other ones have a pKa of about 50. Okay, so we've identified the acid, we've identified the base, we've identified the most acidic proton of the acid, the proton that will be removed by the base, and it's going to give us those products. All right, we're ready to calculate the equilibrium constant for the reaction. Is this reaction going to give a big percent yield or isn't it? So this is an ester. The pKa of an ester, according to that table, is 25. This is water, the acid on the right-hand side. The pKa of water, according to that table, is 16. So the equilibrium constant here will be 10 to the 16 minus 25. That's 10 to the minus 9. So what this is saying is that an ester is not acidic enough to be deprotonated to function as an acid with hydroxide, right? Because this is a lousy equilibrium constant, 10 to the minus 9. This is saying that we mix these two together, we're going to get very, very little product formation. So the equilibrium constant for that reaction is small. All right, so let's try another one. What about something like this? I want a concrete example here. Plus all right, so there's another acid-base reaction. Let's figure out what the equilibrium constant for this reaction will be. First step, identify the acid, identify the base. The base is something that picks up a proton. This guy has a negative charge. It finds a proton very attractive because positive love negative, that's the base. All right, and so this guy must be the acid. Next step, find the most acidic proton on the acid. Go to that pKa table, match up every proton in the acid to an entry in that table, and we find that the most acidic proton is this terminal alkyne proton, pKa of 25. All of the other protons in this molecule are protons bonded to sp3 hybridized carbons, but they aren't any of those special types that we've already alluded to. Okay, so now we can predict the products of this acid-base reaction. That terminal alkyne proton will be removed. H plus goes away. And where did that H plus go? It went over here to the base, which was converted to this amine. All right, so those are the products of the acid-base reaction. And now let's write up our equilibrium constant. All right, the pKa of the acid on the left is 25. The pKa of the acid on the right is 35. I'm getting these numbers by cruising around that table and finding the match to the most acidic proton. So the equilibrium constant for this reaction will be 10 to the 35 minus 25 is equal to 10 to the 10th. So that's a pretty good, pretty big equilibrium constant I can expect 100% yield of product, right? It's not actually 100%. It's really 99.9999999. That's 10 nines%. But, you know, it's essentially reaction goes to completion. All right, finally, let's look at one more example of this acid-base of the calculating the equilibrium constant of an acid-base reaction, but maybe one that's not as, or the identification of the acid and the base is not as obvious. And the situation that most comes to mind is when an amine is a base. So we could have something like a carboxylic acid, and now going to react that with an amine. So something like triethylamine. And this is an acid-base reaction, and we want to figure out what is its equilibrium constant. Okay, here identification of an acid or a base, acid and the base is not, it's a little bit more complicated than the examples that we've done heretofore, because in everything else, all of our other examples, we were looking for something with a negative charge to function as the base. Here we don't have a negative charge. But this problem is a little bit simplified in that we recognize this is the carboxylic acid, right? So this guy must be the base. So this is the acid, and this guy must be the base. But an important thing to remember about amines is that amines are basic. They have this unshared pair of electrons that can reach out and grab a proton from an acid. Okay, so amines are bases. So we've identified the acid. That was the carboxylic acid. We identified the base. I'm telling you that an amine is a base. And so that would be the products of this acid-base reaction. Okay, so now we're ready to calculate the equilibrium constant. The pKa of the acid on the left is 5. The pKa on the acid on the right, this is 10. I'm getting that from that pKa table, right? There's an acid on the left-hand side of this equation. There's an acid on the right-hand side of this equation. Obviously, this guy with a negative charge is not going to be the acid, right? That's going to be the base on the right-hand side of the equation, because O minus, this is not going to give up a proton. This is going to pick up a proton from somewhere, from this guy. All right, and so the equilibrium constant here is equal to 10 to the 10 minus 5 is 10 to the 5th. So that's a pretty respectable equilibrium constant. We're going to get pretty much 100% yield of product. So this is what happens when a carboxylic acid gets together with an amine. We have this swapping of the protons to make a carboxylate and an ammonium ion. Okay, so those are some things that, that's another thing that we can do with the table of pKa's. We can calculate the equilibrium constant of an acid-base reaction. All right, I want to talk a little bit about some of the entries on that table and try to explain why some of them are as they are. We talked about these special sp3 hybridized carbons. We talked about these special sp3 hybridized carbons whose acidity varies all over the place depending on what their neighborhood is. I'd like to talk about why that is. Okay, so why is a bis alpha proton so acidic versus a ketone? Question. So the issue I'm trying to resolve here is we have a proton which is on an sp3 hybridized carbon sandwiched in between two carbonyls. This is considered the, I wrote beta here, but this should be bis alpha. Bis means twice. This is the bis alpha proton. It's the proton sandwiched in between two carbonyls. And when a base comes along, and it removes that proton, base minus is converted to H base. What we get is the removal of that bis alpha proton to give something that looks like this, versus the situation where we have a proton that is not bis alpha, but rather it's just a proton which is sitting next to the carbonyl carbon of a ketone. And once again, we add base, H base is produced, and what we get is that H plus went away and we got, it's minus. All right. So why is this pKa 10 and why is this pKa 20? So this is 10 order of magnitude difference in the acidity of a bis alpha versus a ketone. All right, and the explanation for this is resonance. This guy up here has several resonance structures. So there's one resonance structure where I've taken this negative charge, moved it here, and kicked out that double bond. And then I can have another resonance structure where I'm restoring these double bonds and kicking out this double bond. And so I get 3 resonance structures for this conjugate base, versus down here where I can only write 1 resonance structure. Which looks like that. So remember that resonance is stabilizing, and removal of this bis alpha proton produces a species that has more resonance, more stabilization than the removal of a ketone proton, which has less resonance and less stabilization. So the actual structure of this guy, the resonance hybrid, shows that the electrons have a pretty big box to move around in. The resonance hybrid with a partial negative there, partial negative there, partial negative there, versus the resonance hybrid here, which is going to have a smaller box for the electrons to move around here, partial negative there and partial negative there. So the reason the bis alpha proton is so much more acidic than the ketone proton is more resonance stabilization of the conjugate base. The molecule wants to enjoy resonance. It wants to be stabilized so that when this proton is removed, it creates something that has a lot of resonance forms, a lot of resonance stabilization. So it wants to do that. It wants to be able to enjoy resonance. The ketone proton, well, when the ketone proton is removed, we also get resonance stabilization, but not as much. And remember our important concept that a strong acid has a weak conjugate base and a weak acid has a strong conjugate base. So this guy is a stronger acid than this one. This is a weaker base than this one. All right, and so we see that resonance plays an important role in determining acid and base strength. Let's look at another example from that table. Why is phenol a stronger acid than cyclohexanol? All right, so once again, the explanation here is going to be resonance stabilization. So that's phenol. pKa of phenol is 10. All right, this is cyclohexanol. pKa is 17. And so phenol reacts with a base. The base removes the most acidic proton, which is that phenolic proton O-. Cyclohexanol reacts with a base. The base removes the most acidic proton, which is the OH proton, to give us this. And now, once again, we see that this guy, we have all kinds of resonance structures that we can draw for the conjugate base of phenol. So I'm not going to draw all of them, just draw some of them. So this could be another one. Etc. Right? Because there are more resonance structures. Whereas down here, there's no resonance stabilization. So we see why phenol is a stronger acid than cyclohexanol is that when we pop that acidic proton off, we're going to get something that is resonance stabilized. And molecules want to enjoy the stabilization of resonance. When we pop the proton off of cyclohexanol, we get something that has no stabilization. So that proton is much more reluctant to be removed by the base, because when it's removed, you're getting something that doesn't have any resonance stabilization. This negative charge is just stuck here. And again, this is a stronger acid. Phenol is a stronger acid than cyclohexanol. The conjugate base of phenol, this is a weaker acid. And this is a this is a weaker base, and this is a much stronger base. All right, so that's one of the explanation of why some of those numbers are the way they are on that table. All right, another trend in acid and base strength that we should be aware of is that electron withdrawing groups increase acidity. Electron withdrawing groups increase acidity. But the effect is attenuated. Two T's is attenuated by how electron withdrawing is the group. It's also attenuated by how many electron withdrawing groups are there. And finally, it's attenuated by how close to the site of deprotonation. Well, these attenuating effects are nothing new. We've seen all of these same, we've seen the same effect when we were talking about the NMR chemical shift, right? The chemical shift of the proton, it is affected by electron withdrawing groups. It is sent downfield by an electron withdrawing groups, but the amount by which it is sent down depends on how electron withdrawing the group is, how many there are, and how close they are to the observed proton. So this is nothing new, these attenuating factors. We've seen all of these before. Okay, so this is another one of our trends in acidity and in basicity. All right, so let's look at some examples here. If we look at trifluoroacetic acid versus plain old acetic acid, and we go into the laboratory and measure the pKa's of these two materials, we see the pKa of trifluoroacetic acid is 0, and the pKa of acetic acid is about 5. So what we're seeing here is that electron withdrawing fluorine has increased the acidity over a model compound that doesn't have any fluorine by a lot, by 5 orders of magnitude. But in this case, fluorine is very electron withdrawing. There are many fluorines, and they are very close. They are close to the site of deprotonation. So this is another trend that we see in acid and base strength. All right, so this is called the inductive effect, right? Electron withdrawing groups increase acidity. Let's just make a note of this. This is called induction, or the inductive effect. All right, so let's explain the inductive effect. Induction explained. Trying to anyway. All right, so let's look. We know that the proton of an alcohol is nominally about 17. So let's look at a molecule that has, maybe this guy. And let's versus a situation where we're going to add an electron withdrawing group, such as fluorine. And we want to explain why it is that this guy is going to be more acidic and why this one is going to be less acidic. Right, we have electron withdrawing groups increase acidity, so this one is going to be more acidic than that one. Well, now when we add a base to this and remove the most acidic proton, we get that. Okay, so I'm not finished drawing the structure, but I'm going to make a point about it in a minute. I'm missing a negative charge there, or add it in a second. When we add a base to this guy, once again, we're going to get removal of the most acidic proton. I'm not finished drawing that structure. I need to add a negative charge on it. And I've withheld drawing that negative charge on there for a reason, and that is, see, fluorine is electron withdrawing. Fluorine is sucking electrons away from the atoms that it's bonded to. This guy doesn't have any electron withdrawing fluorine. So there's nothing that is removing electron density from the negative charge that I'm about to write here. So see, this fluorine is withdrawing electron density. I'm going to symbolize that with that little arrow, meaning electron density is being removed. So now when it comes time, finally and at last, to draw that negative charge on that oxygen, what I'm going to do is I'm going to draw a big, huge, humongous negative charge on that oxygen, showing that there is nothing sucking that negative charge away. Down here, that negative charge on this oxygen is now diminished by the fluorine, which is sucking electron density away from all of the atoms that it's bonded to. So the negative charge I'm going to draw here, I'm going to make it much smaller, right? So now, who is the weaker base? If you're the proton here, you're the proton, and let's say you're thinking, there's your thought bubble, whom do I like more? Well, if you're a proton, you like negative charge, and if you're a proton, do you like more negative charge or less negative charge? Oh, if you're a proton, you like this big, huge negative charge over here much more than this wimpy little negative charge over here. So the proton likes this big negative charge. This guy is the stronger base. It's just more attractive to a proton because there's more negative charge on that oxygen. This guy is the weaker base because the negative charge there has been diminished, withdrawn, sucked away by the fluorine. A weak base has a strong conjugate acid. A strong base has a weak conjugate acid. And so we see that this is the explanation of why an electron withdrawing group increases acidity, because an electron withdrawing group is going to diminish basicity. It's going to make for a weaker base, and that counterpart is a stronger acid. Now, we see that electron withdrawing groups increase acidity, and the effect is attenuated by how electron withdrawing the group is and how close it is. So maybe we can look at a ranking problem. Most acidic. All right, so we could put in, let's put in a bunch of carboxylic acids. Let's put in a bunch of carboxylic acids, maybe 4 of them. All right, so something like that. What if we were to rank these in order of acidity? Well, halogen is electron withdrawing because it's an electronegative atom. And we see this guy has more electronegative atom closer to the site of deprotonation. So this is going to be the most acidic one. Okay, of the remaining guys, this halogen and this halogen are equally far from the carboxylic acid proton, but we know that chlorine is more electronegative than bromine, so that this guy is going to be more acidic than this one, and this guy doesn't have any electron withdrawing group, so that would be our standard of comparison. So the acid and base strength is an electron withdrawing group increases acidity, but that effect depends on how electron withdrawing the group is, how many there are, and how close they are to the site of deprotonation. If you think that the only electron withdrawing group out there is halogen, well, it's not. There are lots of electron withdrawing groups in organic chemistry. It's not going to be fluorine all the time. So let's make a little catalog of what the electron withdrawing groups are so that we can be on the lookout for them. Electron withdrawing groups. That takes a long time to say and to write. I'm just going to write EWGs. It's not going to be halogen all the time. It's not going to be fluorine all the time because there are a lot of electron withdrawing groups. All right, of course, halogen, right? Fluorine, bromine, chlorine, and iodine. These are electron withdrawing groups. But we have others. The carbonyl group is an electron withdrawing group. And this is because the carbonyl group has a resonance structure that puts positive charge on the carbonyl carbon and negative charge on the carbonyl oxygen. The actual structure of the molecule is a composite of these two resonance structures. That's not really a single bond. It's not really a double bond. And this carbon has partial positive charge. This oxygen has partial negative charge. Electrons are negative, so that the carbonyl carbon has a partial positive charge and is attractive to an electron. It withdraws an electron. So the carbonyl group is an electron withdrawing group because it has a partially positively charged carbonyl carbon, and positive loves negative and electrons are negative. So electrons are going to be withdrawn by a carbonyl group. Another electron withdrawing group would be the cyano group or the nitrile group, for the very same reason, is that we have a resonance structure in which we can put a positive charge on the nitrile carbon, a negative charge on the nitrile nitrogen. The actual structure of the cyano group is a composite of these two resonance structures where the nitrile carbon has partial positive charge, so that the nitrile group is an electron withdrawing group. because it has this partially positively charged nitrile carbon. It's not going to be halogen all the time. All right, another electron withdrawing group that we see very frequently would be the nitro group. Oh, that is very electron withdrawing. It's much more electron withdrawing than fluorine is, because it has that fully positively charged nitrogen atom, and positive charge is electron withdrawing. And nitrogen and oxygen, these are all very highly electronegative atoms, so the nitro group is extremely electron withdrawing. Another electron withdrawing group that we encounter, maybe not so much until you take biochemistry, would be the ammonium group. That is electron withdrawing. Of course it is, because electrons are negative, they are attracted to positive charge. A positively charged nitrogen is electron withdrawing. So the presence of any of these groups are going to increase acidity of the conjugate acid. They're going to decrease basicity of the conjugate base. Dialkyl sulfonium is another electron withdrawing group that we meet quite a bit. So these are some of the most important, see, have I forgotten any? I think not. These are the most important electron withdrawing groups. It's not just going to be halogen all the time. All right, so let's go back to a ranking problem and use that information that I just gave. If you're lucky, someday you'll take biochemistry. And when you study biochemistry, undoubtedly you will study the amino acids, which are the building blocks of proteins. So which is more acidic? An amino acid all right, this is the amino acid glycine, or a carboxylic acid, right? This is a carboxylic acid. Which is more acidic? Well, in this table I just gave you, we listed this positively charged nitrogen as an electron withdrawing group. It's going to suck electrons away just like a fluorine would. So who's more acidic? An amino acid is more acidic than a carboxylic acid, because the amino acid has an electron withdrawing group, whereas the carboxylic acid doesn't. So the pKa of an amino acid is about 2, whereas the pKa of a carboxylic acid is about 5. So the amino acids, the building blocks of proteins, are more acidic than regular carboxylic acids because of the presence of that electron withdrawing ammonia. All right, so maybe let's try another ranking problem, and then we're going to switch to something else. How about some 4 cyclohexane rings and a partridge in a pear tree? Okay, and I'm going to put an alcohol up here at 12 o'clock. All right, and then I'm going to decorate maybe something like this. Okay, rank 1 is most acidic. So what would be the rank order here? Well, the carbonyl group is an electron withdrawing group. Electron withdrawing groups increase acidity, but the effect depends on how many electron withdrawing groups there are, how close they are to the most acidic proton, and how electron withdrawing they are. Okay, so who is going to be the most acidic proton? This guy has electron withdrawing carbonyl, so does this one, so does this one. This one has 2 of them. This one doesn't have any electron withdrawing carbonyl group. That is going to be the least acidic one, because all of the others have an electron withdrawing group that are increasing acidity. Okay, this guy has 2 of them. So this one is going to be the most acidic alcohol that's up here. And between these 2 guys with 1 apiece, but this one is closer to the site of deprotonation. This one is closer to the most acidic proton, so that's going to be 2, and that's going to be 3. All right. So now in the time remaining, I want to talk about a different topic, and that is going to be some of the chemistry of the alkyne. Alkyne chemistry. All right. So the alkyne is sort of like the big brother of the alkene, in that the alkene has carbon-carbon double bond, but the alkyne has a carbon-carbon triple bond. And so there is a complementarity between these 2 functional groups. Many of the reactions that are entered into by an alkene are also typical alkyne reactions, but that extra bond of an alkyne makes things a little bit different. So I want to talk about a few of the reactions of the alkyne. First reaction is hydrogenation. If we take an alkyne and react that with hydrogen in the presence of a precious metal catalyst such as platinum or palladium, what happens here is that the carbon-carbon triple bond is taken down to a carbon-carbon single bond, and the atoms of hydrogen add across where the triple bond used to be. So I guess I'll put, we don't need to say excess, but we will. What happens here is the carbon-carbon triple bond is completely degraded to a single bond, and so the triple bond gets knocked out and it's converted to an alkane. So a concrete example of something like this would be, for example, if we were to take this phenylacetylene, react that with excess hydrogen over a platinum catalyst, our product of the reaction here would be ethyl benzene, where that carbon-carbon triple bond has been completely reduced to a carbon-carbon single bond. Another example would be maybe this guy. Excess hydrogen and a platinum or palladium catalyst. We would get this alkane, where that carbon-carbon triple bond has been reduced to a carbon-carbon single bond. So this is hydrogenation of the alkyne. Let's talk about the mechanism. We have our catalyst surface, which we're just going to represent like this. This could be the platinum or the palladium surface. And we dose it with hydrogen, gas, excess hydrogen. And the hydrogen undergoes a reaction called dissociative adsorption, where the hydrogen bond breaks, and now the hydrogen is attracted to the metal surface. So this hydrogen bond breaks, and now we have a bunch of hydrogen stuck to the surface of the catalyst. Okay, so now the alkyne comes along. And it also undergoes dissociative adsorption on the catalyst surface. So let's see, our catalyst surface looks like that. There's a bunch of hydrogen stuck to the surface of the catalyst. And now, see, this hydrogen, it was a single bond. And that single bond between these two hydrogens got taken down to a nothing bond. The hydrogens aren't bonded to each other anymore. They're bonded to the catalyst now. Well, the very same thing happens to the alkyne, is that this triple bond is taken down one notch to a double bond. Just like this single bond in hydrogen was taken down to a zero bond, this triple bond is going to get taken down to a double bond, and these carbons get attached to the catalyst surface. So what used to be a triple bond is now a single bond, looking like that. So this is the dissociative adsorption. The bond breaks down by one notch, and the atoms in that broken down bond get hooked up to the catalyst surface. Okay, and so now this looks like an alkene. This reacts with this hydrogen. It reacts with some of the hydrogen that's on that catalyst surface. To form a cis alkene, right? It's cis because the hydrogen, the carbon atoms picked up the hydrogen from the catalyst. The catalyst is down here, so both of these hydrogens were added in a cis manner. Okay, so the triple bond has been taken down to a double bond. Now that double bond, this guy, adsorbs on the catalyst surface yet again in a dissociative adsorption event, which is just like the other two that we've considered up to now. This double bond is going to be taken down to a single bond, and these carbons end up bonded to the catalyst surface. So we have a hydrogen there, we have a hydrogen there, but now this alkene, that double bond was degraded to a single bond. and the carbons are bonded to the surface. And now these carbons pick up these protons, these hydrogen atoms from the catalyst surface. And there is our final product, which is an alkane. So that's the mechanism for how a double bond, how a triple bond is taken down to a single bond by hydrogen adsorbed on a catalyst surface. All right, it would be nice to be able to stop the reaction at the cis-alkene stage. And indeed, that is possible using a similar system, which is that of a poisoned catalyst, a deactivated catalyst. And that is called the Lindlar catalyst. Using the Lindlar catalyst. And this is palladium plus barium sulfate plus a tertiary amine. You don't have to know the recipe for the Lindlar catalyst, but that's what it is. Using the Lindlar catalyst plus hydrogen stops the hydrogenation at the cis-alkene. So if we were to take an alkyne, react that with hydrogen and Lindlar palladium, we just saw in the mechanism, we just saw in the mechanism. Can I change this to a CH3? Can I change this to a CH3? The product stops at the cis-alkene stage because the Lindlar catalyst is a deactivated or poisoned catalyst. Lindlar palladium is deactivated. Or we also call it a poisoned catalyst. It's not that barium sulfate and that tertiary amine make it less active so that the second stage of hydrogenation can't happen. That triple bond is taken down to a cis double bond, but it can't be reacted any further than that. It would be nice to be able to produce a trans alkene from an alkyne. We know how to make a cis-alkene from an alkyne. We use that hydrogen and the Lindlar catalyst. It would be nice to know how to make a trans alkene from an alkyne. And indeed, there is a way, and that is the dissolving metal reduction. Dissolving metal reductions of the alkyne make trans alkenes. All right, so the overall reaction is going to be, you start off with an alkyne. You have two equivalents of a metal, and this is always going to be a group 1 metal, lithium or potassium or sodium, and 2 moles of ammonia. The product is going to be the trans alkene. So this is a way of making a transalkene from an alkyne. All right, so I want to talk about the mechanism of this reaction, how exactly this works. It's quite involved. So the alkyne, that's just the traditional, conventional way of writing an alkyne, but let's change it up a little bit. You see these lines here? See all of these lines here? They're bonds. And what is a bond? A bond is a shared pair of electrons. So try to make this mechanism, it's pretty complicated, a little bit more understandable. Instead of writing the alkyne in that traditional way, I'm going to rewrite it this way, where I've replaced one of the bonds in that triple bond by 2 dots. Well, that's fair because each of these lines in the chemical structure is a bond, and a bond is a shared pair of electrons. I just replaced the conventional line with two dots. Okay, so now the first step of the mechanism is the metal, the lithium, sodium, potassium, or lithium, sodium, or potassium. Those are all group 1 metals. They have a single electron on them, right? Lithium, that's group 1. So is sodium, so is potassium. There has 1 valence electron. And so one of the things that we learned in Gen Chem is that atoms want to adopt an inert gas configuration. They want to become a group 8. They want to look like a group 8 element because that has the closed shell. That's the inert gas, the noble gas configuration. So this lithium atom or sodium atom or potassium atom wants to get rid of that electron. And so what it is going to do is it's going to donate its electron to this triple bond, and in the process become a positive 1 ion. Where did that electron go? That electron went to one of these carbon atoms, right? And so we get this thing which is called a vinyl radical anion, where the metal has been stripped of its electron. It wanted to get rid of that electron so it could become like a group 8 element, and it has donated it over here to this bond, to this triple bond, to give this radical anion. This is a pretty strong base. And so what happens next is that our first equivalent of ammonia functions as an acid, and that C minus removes the proton from ammonia. If we want to use arrows, we could do something like that. This is an acid-base reaction. And here we have this radical. Okay, now this carbon here, he's not very happy. He's a radical. We know that radicals are unstable because they don't have an octet. So now our second equivalent of metal ion gets involved. And once again, this lithium atom or sodium atom or potassium atom or whatever it is, it wants to get rid of that electron. we have a carbon atom that wants to pick up an electron. So it's a great situation. This, the metal atom gives up its electron to that carbon. And where there was one dot, now there are two. And this guy here, which is called a vinyl anion, it turns out that he is configurationally unstable, in that this guy is actually undergoing a conformational change in which that R group can be either that way or sort of linear or this way. Right, so when we were studying radicals, we made the point that some radicals are undergoing a conformational change, the radicals that aren't stabilized by resonance. Well, this is sort of similar in that this species undergoes this equilibrium. This guy here, he's actually a transition state. So that R is flipping back and forth, back and forth, back and forth, back and forth. So if we consider these two guys, we see, oh, this one is more stable. There's more of it. Why? Because the R groups, the R's are trans and they're out of each other's way. So that's what predominates in the reaction mixture. Last step of this reaction mechanism is the second mole of ammonia gets involved here. It undergoes this deprotonation. It functions as an acid. And there's our trans alkene. So just to summarize what we have said for these reactions of the alkyne summary, we have an alkyne. We can do a couple of different things to it. We can add hydrogen and platinum or palladium. Excess. We're going to get total reduction of that triple bond to a single bond. Or we could add hydrogen and Lindlar palladium. That is going to give us the cis alkene. The Lindlar catalyst is a poison catalyst. It is deactivated, so we won't get the alkane. Or we could use this dissolving metal reduction. 2 moles of lithium or 2 moles of sodium or 2 moles of potassium and 2 moles of ammonia. And we just went through the mechanism of how this is a way of getting a trans alkene. So this is going to be cis and this is going to be trans. And this is, so these two ways are ways of making an alkene. And so if we wanted to, these could fit in to the reactions of the alkene that we have been studying.